So welcome back. Today we are going to discuss about some interesting parts of quantum computing. So quantum information versus classical information. What is that? Quantum information versus classical information. So let's understand how information in quantum world is completely different from what we use in our everyday computers. Okay. So moving on to the introduction. So classical computer works with bits. Okay, they can be either 0 or 1. This point you need to remember. So whereas quantum computers use qubits, they can be 0 they and both at once. Already in the earlier video I have explained, we call it as superposition. So this special ability gives, okay, the computers their amazing power. Instead of searching every algorithm or everything one by one, the what does quantum computer do is nothing but it do at once. That we call it as superposition. Okay, so you can think of like this. Okay, a classical bit is like a light switch, either it will be on or off. But a qubit is like a spinning coin, it will be both heads and tails until you look at it. Okay, so that's the key difference between classical computer and as well as quantum information. Okay, so the basic unit of information. So in classical computers, information is stored in bits, which can only either 0 or 1, as I discussed earlier in this particular video. Okay, but whereas in quantum, so the basic unit of qubit is written as alpha ket 0 plus beta ket 1. So if you are not familiar with ket 0 ket 1, please refer the please refer the old video that I have created on quantum gates. Okay, so where ket 0 is nothing but 1 0, ket 1 is nothing but 0 1. So it should obey this condition, then only we can say the qubit is valid. Okay, mod alpha square plus mod beta square, it should be is equal to 1, where alpha and beta, you already know, they are complex numbers, which tells the probability of qubit being in 0 or 1. So if we add up those probabilities, so that should be equal to 1. So in simple words, a qubit is a mixture of 0 and 1 until we measure it. So until we measure it, so it will be either 0 or 1. Okay, so I have listed some differences, some major differences between classical and quantum information. So that is nothing but classical information can be definite like it is either 0 or 1, but whereas qubit, it is superposition of 0 and 1. So classical bits are represented by voltage, okay, or current, while quantum information uses tiny particles. What are those tiny particles? Photons or electrons. Okay, so this you need to remember. So classical computers do one task at a time. Okay, do one task at a time, whereas quantum computers can process many possibilities at a time. So it is due to the superposition. Okay, copying in classical system, you can freely copy the information. Okay, and whereas in quantum, you cannot copy the information due to no cloning theorem. It would destroy its delicate state. Okay, that is the reason you need to mention this no cloning theorem. Okay, classical outputs are predictable. Okay, that is, we call it as deterministic is nothing but future is fixed, whereas quantum will be getting only the probabilistic output, or we can say probabilities. Okay, in classical we'll be using logic gates such as and, or, not, nor, exam, etc., that I have discussed in earlier videos. Okay, but whereas in quantum gates we'll be using poly x gate, poly y gate, poly z gate, Hadamard gate, C0 gate. I haven't listed some gates here. You can also write that gates in this particular, okay, point. Okay, so moving on to the eighth point. So data is stored in zeros and ones. Okay, but whereas here data will be stored in wave amplitudes. Okay, that you need to write. So moving on to the ninth point, classical computers use electric signals, okay, for communication, whereas quantum computer uses photons, okay, and it uses entanglement, okay, the particles that remain connected even they are far apart, that you need to write. So classical data can be hacked or intercepted, but whereas quantum idea or quantum data is automatically secure using the method called quantum key distribution. I will make a video on quantum key distribution. Quantum key distribution says that if anyone is trying to hack our system, it can not happen, because if we measure a qubit which is in superposition, the qubit collapses. That is the reason behind the quantum key distribution, okay. So the error correction is in classical systems is simple, but error correction is much more complicated in quantum, okay. So this point you need to write. So classical bits don't show interference. Interference is nothing but the combinedly moving waves, okay. Two or more waves combinedly move, we call it as interference, whereas in quantum interference we can observe, okay. So bits are easy to scale, whereas qubits are sensitive. We can say it is as fragile or fragility, which gets disturbed easily. This is the problem. So we call it as decoherence. Decoherence is nothing but if any disturbance comes from the environment, which the qubit is in superposition, it will be disturbed, okay, and it will lose its state, okay. That is the meaning of decoherence, okay. So which is finally, so classical systems are in our laptops and phones, but whereas quantum systems live in labs. So some companies are focusing, such as Google, IBM, and Google Sycamore, Microsoft QHash, PsiQuantum. So these are the companies that are focusing on our quantum. So this is how we can say, this is the differences. By these differences we can say quantum systems are powerful but delicate. That you need to remember, but delicate, okay. So moving on to some mathematical representations, again have included all those things for your understanding. So classical bit, okay, ket 0 is equal to 0 1 1 0, and ket 1 is equal to 0 1. So it is represented as alpha ket 0 plus beta ket 1, okay. So here in classical bit, in if you check a bit, it says the same. Let's say it is 0 or 1, but in quantum computers, when you measure a qubit, okay, when you are trying to measure a qubit, it collapses either to 0 or 1. That is the small difference. That is not small difference, that is a big difference, okay. The act of measurement changes the qubit state, okay. It's like catching that spinning coin. Once you look, it stops spinning and show either it heads or tails, okay. You lost the original superposition. That's why measurement is tricky in quantum mechanics. That is what about the measurement, okay. So copying the information, classical data can be copied. You can duplicate a file or copy a signal, but quantum information follows the no cloning theorem. What does no cloning theorem say? You can't make an exact copy of unknown qubit, okay. Why? Because copying it would destroy the delicate quantum system. This is actually good news. It makes quantum communication extremely secure, okay, because no hacker can perfectly copy quantum data. That is why copying and quantum is very secure, okay. Moving on to entanglement, I will quick recap. Entanglement is like a quantum friendship. When two qubits become entangled, changing one automatically affects the other, even they are kilometers apart, okay. For example, this is the combined state, okay. Ket psi is equal to 1 by root 2 ket 0 0 plus ket 1 1, means if the first qubit is 0, what I am saying, if the first qubit is 0, second qubit is also 0. If the first qubit is 1, the second qubit will be also 1 in this particular scenarios. Okay, that is what we say. Einstein called this as spooky action at the distance. Okay, spooky action at the distance. It's a key ingredient for quantum teleportation and as well as quantum internet. Okay, so security, I am talking in point of security. So quantum key distribution. So in classical cryptography, keys are shared digitally and hackers can interpret them. Okay, digitally the keys will be shared, the keys of your WhatsApp end-to-end encryption, everything will be shared digitally and hackers can see them and interpret them. Okay, but in quantum system, keys are sent using photons. Okay, using photons, this you need to remember, using photons, which is in superposition states. If one tries to spy or one tries to hack, okay, measure them, the quantum states collapse. Okay, revealing the institution immediately, that is nothing but revealing someone is eyeing on our system. Okay, that is what the meaning. So this is called quantum key distribution or QKD in simple way. It makes quantum communication ultra secure. So one famous example, that is nothing but BB84 protocol. It is developed by Bennett and Brassard in 1984. I will explain. I will make one video on BB84 protocol and even quantum communication and quantum key distribution. Okay, combinedly I will make a video for that. So moving on to quantum parallelism. Okay, so classical computer test one input at a time. For example, checking password one by one. So it takes much time, right? So whereas quantum computers can use superposition to test many possibilities at once. So this is why they are so good at optimization, searching and as well as cryptography. Okay, a great example is Grover's algorithm, which can find one item out of millions in just the square root of steps needed by a classical computer. Okay, so please note this particular point. So Grover's algorithm also, it is one of the interesting algorithm. In future I will make videos on Grover's algorithm also. Okay, so visualization point of view, so a classical bit is like a light bulb. Okay, I'm saying very simple, that's either on or off. But a quantum bit is like spinning bulb. Okay, that glows on both on and off at the same time until you observe it. Okay, classical computers are predictable, you always know what you will get. Okay, that is what definite and predictable. So quantum computers are uncertain, so you but have a lot of power. Okay, uncertain but powerful. So quantum computer does not replace classical ones, they work together solving different types of problems. Okay, that you need to remember, this point you need to remember. Okay, so thank you guys. Okay, if any questions, let me know in the comment section.